to the first tutorial of the textbook Statistical Rethinking of the class Multivariate Analysis lectured by. In this chapter, the author wants to illustrate the following idea. Our posterior will be equal to the prior times the likelihood. And the author is curious about how much of the surface of the Earth is covered in water. So he did a kind of ridiculous experiment by throwing a globe up in the air, and when he catches it, he recorded whether or not the surface under his right index finger is water or land. And after 9 throws, he got the data. The first throw was water, the second one was land, and water, 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 land, water. So in summary, it's like 3 waters and 3 land. So in this chapter, we will learn about how we can use this data to find out the P. Firstly, we have to construct a model which describes the data generating process of these 6 water, 3 land data. And then we have to fit this data into the model we have constructed, and then use different approaches to estimate the P. And these different approaches include grid approximation and MCMC. And these 2 methods will be introduced in this chapter. The model, and what is the data generating process in this experiment? Actually, it's a very simple binomial distribution. So the proportion we get water is the proportion of water on the globe. And so the distribution of water and land are distributed binomially with P representing the proportion of the water on the Earth. Our model, and the next step is to fit the data into the model and then to find out the best value, or we can say the most probable value of P. So there are different methods for us to estimate which P is the best. And in the textbook, the author said there are 3 ways. First, grid approximation. Second, quadratic approximation. And third, MCMC. And in this class, we will only talk about grid approximation and MCMC. So let's get started from grid approximation. And what is grid approximation? Actually, the intuition is very simple. So we know that the P can only lie from 0 to 1. And the intuition of grid approximation is to try every possible value of P in this region and find out which value is the best P with the maximum likelihood to generate such a data, which is the 6 water and 3 land data. However, we all know that there are infinite values in the region of 0 to 1, so we have to choose some values between 0 to 1, and these values are our grid. And then we can define the weight of every P in the grid we choose because we may have some prior information about the P. For example, we may know that there are more water than land on the globe, so we can give a higher weight for the P larger than 0.5. And with this prior and likelihood, we can just multiply them together to get our posterior. It may be a little bit complicated from what I have said, but it will become easier to understand once we started to look at the codes. So firstly, we can construct our grid by choosing the P from 0 to 1. So the sequence function will allow us to do this. We just choose 100 values from 0 to 1. You can see from 0 to 1 with 100 values. And then we can assign the weight, which is called the prior of each P value. And here we assign a uniform prior, which means we don't have any prior information about the distribution, the proportion of water and land on the Earth. So we give equal weight to each P. And with this, we get the data frame like this. So the third step is to calculate the log likelihood. And we use the D binomial function, and this function will help us to find out the likelihood when our probability is P and our data is like 6 waters from 9 draws. Result will look like this. So we can see that if our P is 0 and the likelihood of getting 6 water from 9 draws will be 0, and as the P goes higher and higher, the likelihood also goes higher, and at around like P at around 0.7, 0.7 or 0.6, the likelihood is very high. And after that, it will start to decline as well. And when our P is 1, which means 100% of the globe is covered in water, and the likelihood will be 0 again. For now, you can see that we have already our prior and our likelihood. We can just multiply these two columns to get our posterior. Okay, so we got our posterior value, but notice that there is a small problem in these posterior values. Since we want to know the possibility of each p, we would expect this posterior value to sum to 1. However, this is not the case because the prior is not sum to 1 and the likelihood is not sum to 1 either. So we can check the result by. Okay, so we got our posterior value, but notice that there is a small problem in these posterior values. Since we want to know the possibility of each p, we would expect this posterior value to sum to 1. However, this is not the case because the prior is not sum to 1 and the likelihood is not sum to 1 either. So we can check the result by extrapolating this code. We will see that the posterior we just calculated has a sum of 9.9. And how can we do that? It's actually quite simple. We just need to standardize the posterior by dividing each posterior value to the summation of each, and the result will look like this. So for now, the grid pos will be exactly what I want with the sum of 1. Okay, and the next step is to plot this result using ggplot. We can use a line plot with x-axis representing each value of in the p grid and the y value of the posterior value. So we can see that the highest possible value of p in the p grid is around like 0.6 to 0.7. The second approach is called MCMC, and which is done through coding a STEM program. So what is MCMC? And basically, it's an algorithm to help us estimating our parameters. In this case, the proportion of water P. And how does it work? And simply speaking, MCMC will draw lots of samples and to form the posterior. And we just need to count the samples just need to count the results to know the posterior. So let's start to build our first STEM model. Recalling tutorial 0.3, any STEM model has 3 parts: the data, the parameters, and the model. So what is our data? It's very simple. It's like the rows we have, like 6 water and 3 land. So we have data is how many rows we have, and the second one is how many waters we have. So it's just 6, and this is just 9. And the parameter will be the proportion P. And we set the limit of the proportion since it will certainly lies in the region of 0 to 1. And by setting the region, STEM will runs better. And the last part is the model, and which will be the same as our the data generating process. So it's a binomial distribution with n experiments. P will be the proportion. And then we can also, this is our model. Also, we need our prior regarding P. So as what we did in grid approximation, we set equal weight to each P value. Here, we do the same thing. So we assign an uniform prior to our P. So uniform 0, 1 means that, P, the possibility, our prior knowledge on P will be any value between 0 to 1. So this is our STEM model. That's our model here and run. So the data we will provide will be at least n equal to 9 and water equal to 6. And we just go the STEM function and run the program. After fitting the model, we can check the result first. We can see that the mean is about 0.63 and the median is about 0.64, which are very close. And also STAN provides us with the 2.5%, 25%, 75%, and 97.5% percentile. But this point estimate is not what we care about the most. What we care about is the whole distribution of the values. We can use the s.data.frame function to extract the posterior from the STEM model. The result will be 5,000 rows of P, and each P will be the result of one iteration of MCMC. But looking at this data frame, this result is quite different from what we got from grid approximation. In grid approximation, our result will be a probability of each value in the P grid. But how can we compare this result with the count of samples we got from MCMC? So the first thing we need to do is to calculate the count of samples from this result, from this 5,000 rows data frame in each P grid interval. So I can use the hist function and with a customized breaks. And these breaks should be equal to the grid we set for grid approximation. So we again create the P grid from 100 P's from 0 to 1. And then we only want the count of samples in the region, and we don't want the plot, so I set plot equal to false. Then the result will be something like this. Okay, we have our breaks, which is equal to the grid approximation, and we have the count of samples in each interval. But notice that the counts only has 99 values. It doesn't provide us the count of sample in P equal to 1. So we have to add 1 0 at this count data. So we extract the count data from the hist result and then concatenate. The result will be a 100 values vector. And then we can calculate the relative probability easily. So it's just like A divided by the sum of A. And this will be the relative probability of our STAN output. And we can add this column to our result of grid approximation and to make it easier for plotting. So for now, we have the result of posterior from grid approximation and the posterior from MCMC. And then we can use the ggplot to compare the two results. And for the grid approximation result, I will use the line plot, and for MCMC result, I will use a column plot. The aesthetic for x-axis is the same as for P grid, and the y for line plot will be the posterior from grid approximation. For the column plot, we have the same P grid in X and Y equal to MCMC posterior. And the result will be like this. You can tell from this part that the results from MCMC and grid approximation are quite similar, and you may wonder why we need to learn about the complicated STEM programming language and STEM model. But the point is that in this simple case, we can easily set our grid in the region of 0 to 1, but in other cases, like when we have an equation to solve, like a regression problem, the coefficient of each parameters can range from like positive to negative infinite. So there's no way we can set efficient grid to do the grid approximation. This is one thing, and the other thing is that in this case we can use the binomial function in R to calculate the likelihood, but like we may have a very complicated model with a mixture of likelihood function, and it's not possible to or it will be very hard or require very advanced math skill to construct a likelihood function to calculate it. And in this situation, MCMC will provide is a very helpful tool to solve this problem. So this is the end of the tutorial of chapter 2, and hope to see you soon next time.